Gary already gave you a bit of an introduction of myself, breezed through the side pretty quickly. He mentioned I have 20 years experience doing embedded design. Most of my background's in software and project technical lead, done all kinds of small products, embedded products, thermostats, CO detectors, hot water heater controls, all kinds of things. I've been with Ocular for, I think, 7 years now, and I'm a director of product technology, which basically means I'm the touchscreen guru. I'm the guy that's responsible for making sure that all the touchscreens are built correctly, tested correctly, and that the quality of the actual design is good for our customers. We'll talk about the different technologies. We'll talk about the general operating principles. So for some of you that may have looked into some of this technology, some of this may be a rehash, some of it may not. We'll spend most of the time really on Pcap for a couple of reasons. One, selfishly, that's what I happen to know most about. But secondly, it also is the dominant player in the market right now, so it's probably the most important to understand and learn about. And third, it's really the most complex. There are a lot of different options and things that can go wrong, things that can go right. So probably 25–30% of the presentation is on Pcap. But we will talk about the other touch technologies that are available. And then at the end, I'll give a brief sort of overview of how do you pick which touch technology would make sense for you for a particular product. We're not going to talk about sliders, capacitive sliders that I'm sure you've heard about, where you can move your finger, left, sideways, right, up and down, whatever. And we're also not going to talk about capacitive wheels like on the old style iPod that they used to have. We're also not going to talk about infrared sensors, which technically aren't really touch sensors, but just wanted to be clear. We're not going to talk about, urinal sensors and soap sensors and all that kind of stuff. There are a whole bunch of other things we're not going to talk about as well. In particular, let's not bring up the Texas Rangers or Tony Romo, because those are just bad topics to get into. So what we will talk about are projected capacitive, or Pcap. We'll talk about resistive, talk about a digitizer kind of technology, optical touch screens, infrared touch screens, surface acoustic wave, which is also called SAW, and surface capacitance. There are actually another 15 or 20 touch technologies I could probably name off the top of my head, but we're not going to talk about a lot of those. First of all, obviously we have a limited time. And secondly, these are really the technologies that, in terms of the market, that have actually been implemented and have a relatively large user base. So there are other things you'll hear about, like frustrated internal reflection and some of the other things. We're not going to get into those, but you can always Google some of that stuff and find pretty decent stuff on the internet. Most of you, I'm sure, are aware of resistive touchscreens, which have been around for a long time. And until maybe 5 or 10 years ago, resistive was really sort of the only thing out there. There were a few bits and pieces players in some of the other markets, but resistive was really the king of the hill. But then 2007 happened, and I'm sure you all remember what happened in 2007. Apple came out with the iPhone, and suddenly everybody went, ooh, Pcap, what's that? I've got to have that. That's the coolest thing. The iPhone really did two major things for touch technology. One, it introduced the concept of Pcap and made it affordable to the point where other people could start using it in their devices. And secondly, and something that people don't even sort of realize, the iPhone also introduced this concept of a bezel-less design. That is, a design where you have a flat piece of glass on the top, and except for maybe a decorative ring around the edge, there is no raised bezel around it. And in fact, in some of the newer cell phones, there's not even a decorative edge. You can wipe your hand across the entire surface. It's all just one big flat piece of glass. And the interesting thing that we're seeing is a lot of people are being driven to Pcap, not because they understand the technology, but because they want that industrial design. A lot of people talk about the iPhone look. Well, that's really what most people mean when they talk about the iPhone look. They want that flat bezel-less design, which you can't get with resistive, and you can't get with surface acoustic wave, and you can't get with some of the other technologies. I mentioned that was 2007. If you looked at the market in 2007, you would have seen resistive was the biggest thing out there. If you look at the most recent data for 2013, you can see that Pcap has now completely dominated the market. This data comes from a company called Display Search. They focus on touch technologies. And one caveat here, they do tend to focus on consumer products. So these numbers represent mostly cell phones, tablets, notebooks. They do include some embedded products like ATM and casino gaming and some other things. But they don't generally have things like thermostats or fish finders or security keypads, industrial controls. In those kinds of markets, resistive really is the larger player right now, more because of the design cycle times and the lifetimes of those products. I think you'll see those products cycling to Pcap over the next few years. But these numbers don't represent that. They represent more the consumer side. So you can see that Pcap is almost 92% of the market, and resistive is almost 8%, which really doesn't leave much for anything else. So you notice that in the graph that I'm showing, Everything else, other than these two, basically only represents 0.4% of the touch technologies. But those are surface cap, acoustic, infrared, optical, digitizer, and then that plethora of other category that includes all kinds of other little bits and pieces. Now, before we get started talking about each technology, let's spend a second talking about indium tin oxide, because it figures into all of these technologies in almost all of them in one way or another. I'm sure you've all heard of ITO, indium tin oxide. I won't get into a lot of the technical details, but I do want to cover at least a few specific points about it. First of all, it's a transparent conductor, and the way it works is you put it down on a sheet, some kind of substrate, and when you put it down as a solid, you get a resistance in ohms per square, which, if you think about the math and how it works out, it seems kind of strange at first if you've never gone through it. But the way it works is you model it as a series of resistors that are all in parallel as well as in series with each other. And so what happens is, for every square piece, you get a certain resistance. Whether it's an inch by an inch, or it's a millimeter by millimeter, or it's 2 meters by 2 meters, the resistance of that square is always the same. It's when you start making different shapes out of it, rectangles or stars or whatever, that the resistance starts to change. But it's always quoted in terms of ohms per square, because that's really kind of how it works. So the typical resistance for ITO is 100 to 200 ohms per square for most of these touch products. The interesting thing to note here is that the transmissivity, how much light gets through, is dependent on that resistance. So the higher your resistance, the better your transmissivity. Basically, if you think about it, you have to dope it with more conductors in order to get the resistance down. And so the more conductors that you add to it, the less light gets through it, is more light that gets blocked by those conductors, and so your transmissivity actually decreases. So you generally want to have a higher resistance when possible. But of course, that also causes electrical issues. If the resistance is too high and you make an electrode that's this long, well then by the time you get to the end of the electrode, you don't have much of your signal left. So there are trade-offs there you have to balance in terms of the resistance that you're using as well as the size of the touchscreen that you're working with. I mentioned that they get applied to a substrate, so they're typically either applied with vapor deposition or sputtering. That substrate is usually a film material, some kind of acrylic film, like PET is the most common. But you can also put it on glass, and actually most of the touch panels that we build at Ocular are all glass-based. Film is less expensive, obviously, than glass, but you're also going to get better optical quality out of the glass. So it's, again, a trade-off of, which one do I want to use? Am I more worried about cost? Am I more worried about thickness? Am I more worried about optical quality, durability, whatever. Another interesting little fact that you won't find, or at least it's hard to find on the internet, is the thickness of the ITO. The ITO on the substrate is extremely thin. It's measured in angstroms. It's typically anywhere from 100 to a couple of thousand angstroms thick. And the interesting thing about that is that film, because it's flexible, has to have thicker layer of ITO, because as the film flexes, the ITO can tend to crack. So they put a much thicker layer of ITO on film, typically say 1,000 to 2,000 angstroms, than they do on glass, which might only be 100 or 200 angstroms. So that's another reason that you get better optical quality out of glass than film. It's not just because of the substrate, it's because they actually put more of indium tin oxide on the film material than they do on the glass. Okay, so back to the actual touch technologies. Resistive, I'm sure most of y'all have heard of it. You probably, for the most part, know how it works. Forgive me, this is rehashing for you. But in a resistive touch panel, what you do is take two conductive layers of ITO, one on top of the other, facing each other. And when you touch it with your finger, you're actually flexing the top layer of ITO, which then makes contact with the bottom layer of ITO and forms a circuit. You've got voltage sources and meters, essentially, on each of the four corners of that ITO, of the layers. And so you can essentially measure that closed circuit path through the ITO from different directions, and that allows you to triangulate where the finger is located. So it's a relatively simple technology in that you're just making contact, and all you got to do is measure a voltage from maybe 2 or 3 different points. There are a bunch of different ways to do that. The most common and most basic is 4-wire, where you're basically making connections on the corners. There's also 5-wire, where you do connections around the corners and I believe it's the center. And then there's an 8-wire where you're doing corners and center lines on each of them. The reason that you might want to add more connections is that you get a more robust system. So for example, if you have a 4-wire system and you get a break in the film anywhere, even a small one, it essentially ruins the touch panel. You can't use it at all because you can no longer accurately measure the resistance. Whereas if you go with an 8-wire, you can actually measure around defects in the film. So if somebody pushes down with a pen in one particular point and messes that part of the film up, it'll still work in other areas. Generally speaking, resistive is single touch because of the way the technology works, because you're measuring that contact point. There are some companies that have done multi-touch resistive, very low number of touches, 2 or 3, but they're proprietary technology and they use funky connections and weird algorithms. But there is such a thing as multi-touch resistive, it's just not very popular. So the pros for resistive, really the biggest one is that it's inexpensive. It is and has been the most inexpensive option really for touch for a long time. And there are 2 factors to that. One is the fact that the conductive layer is just a plain sheet of ITO, so you don't have to do any kind of patterning or processing on that sheet. All you do is just buy the sheet, put some FPCs around the edges of it, make your connections with it, and then the other place where you save money is that you typically don't need a dedicated controller. Because it's a very simple interface, you can either do it with a simple micro and some A to Ds, or a lot of micros actually have built-in resistive touch controllers in them. So you really don't have to pay any extra for that. So when you get to one of the other technologies that we'll talk about, like Pcap or Surface Cap or whatever, one of the most expensive parts of that is going to be the controller. The controller and then the fact that you have to pattern the layers. So that's one of the reasons that resistive tends to be less expensive than the other options. However, now that Pcap has become so popular and is dominating the market at 91%, the cost in particular of the controllers is coming way down. And so I'd still say that resistive is probably cheaper than Pcap, but the price difference isn't anywhere near what it used to be. Another thing about Pcap, resistive, that makes it popular is that it's a very thin technology. You can get, say a 50 micron PET film with ITO on it, put 2 of those pieces together, and you essentially have 100 to 200 micron thick touch panel. You can do the same thing with Pcap, but it gets a little bit trickier in terms of how you space it and the adhesives that you got to use and all that. But in theory you can do the same thing, but then you've also got to add a controller if you're going to do Pcap. Another thing that is great about resistive in some cases is that you can activate it with anything. You can do what I like to call the poke it with the stick test. You can take a resistive and literally poke it with a stick and it'll work. You can't do that with Pcap. You can't do that with Surface Cap. You can't do that with a lot of the other technologies. In some cases that's bad because you actually don't want things to activate the touch screen depending on what it is, your palm or your whatever. You take a resistive touch panel and put your hand down on it and then also try and use a stylus or pen on it, it's not going to work because you're essentially shorting it out in multiple places. It looks like a multiple touch. So it's not designed to do that. Another positive thing about resistive is it is, for all intents and purposes, really immune to external noise, whether it's noise from the TFT or it's noise from an external source. Because it's just a resistive, you're just measuring the resistance, the current basically through the ITO, you don't really have to worry about any kind of external noise interfering with your system. Now, the downsides of resistive, and this is the reason why it's only 8% now instead of 95% like it used to be, the biggest issue is that it gets damaged very easily. You've all seen those touch panels typically on signage or point-of-sale terminals where people are signing their names and somebody's actually used a physical pin on it and it's dented and there's marks all over it and it doesn't work as well and they have to replace it. That's really the biggest issue with resistive. Going along with that, you also have the issue that the resistance of that sheet changes over time. So I'm sure you're all familiar with, say, 5-10 years ago, you had to recalibrate your touch panel all the time. That was because the sheet resistance itself is changing as the sheet changes and deforms over time, as well as people damage it or occlude it as they mark it up. You also have to worry about temperature and humidity and how that affects the resistance. So that's the main reason that you have to constantly go through those recalibrations. Both of those issues, the fact that it can be easily damaged and that resistance changes, are really inherent in the resistive technology. There's just not a lot you can do about it. So if you really want cheap, you can go with resistive, but you've also got to think about maintenance costs, you've got to think about industrial look if somebody writes on it with a pen or whatever, you've got to think about what the environment is, if somebody wants to clean it with alcohol or some heavy-duty abrasive cleaner, it's not a good idea. There are all kinds of issues that you have to worry about. The last thing I want to mention is something I mentioned before about the iPhone. One of the difficulties with resistive is that you can't really do a bezel-less design because the top layer of it is a piece of film. And that film, you don't want that film to be over the entire surface of your device. So you have to have some kind of bezel around it, some kind of way of clamping it or holding it in place, which means there's going to be some step down to it. Now, again, 5-10 years ago, that didn't bother anybody. But then Apple came out and said, no, you should not have a bezel. And now everybody says, oh, I don't want to have a bezel. So that makes resistive in particular very unpopular today. Okay, now Pcap, which as I mentioned is where we'll spend most of our time. Pcap is, again, the dominant player really in consumer market, as everybody knows, and it's really becoming more and more dominant in the embedded markets and lower-end 8-bit kinds of devices markets. We at Ocular actually mainly focus on embedded industrial controls, and so we get calls from people all the time who want to replace their resistive touch panel with a Pcap touch panel. It's just happening across the board in every market and every segment. A Pcap is typically consisted of 2 layers, and when I say layers, they don't necessarily have to be different physical layers. I really should say probably 2 different electrodes. Those electrodes are made up of some kind of conductive material like ITO, and they can either be on glass or they can be on PET, or you could have a combination. You might have a top layer that's glass and a bottom layer that's PET, or vice versa. Typically with Pcap, what you have is some kind of patterned electrode that is created in that conductive material. And there are different electrode patterns and shapes and sizes, and we'll talk about a couple of those in a minute. But the general idea is you have some kind of electrode shape that you've created on that conductive material. And those electrodes are divided into 2 groups. There's a set of drive electrodes and a set of sense electrodes. The drive electrode is actually driving a square wave down the electrode, or can be other signals. Different companies do different things, but we'll make it simple. We'll talk about it being a square wave. So you drive a square wave down the drive electrode, and then your sense electrode actually picks up that signal and it gets coupled in. And those 2 electrodes together create a capacitor, whether they're side by side in a coplanar arrangement or they're on top of each other in a stacked arrangement. Either way, you get essentially a 2-piece capacitor. So it's projected because the drive signal is creating this electric field, and it's capacitive because those 2 layers or those 2 electrodes form a capacitor. So the touch panel, when it starts up, runs a calibration sequence. It figures out what the capacitance is of each of those intersections. So I have a drive electrode, a sense electrode, they cross each other or they're next to each other. It goes off and measures all of those and figures out essentially what the default capacitance should be for each of those capacitors. Then when your finger touches it, it actually drains off a little bit of that energy and changes that capacitance. So it does another measurement scan, it figures out the new capacitances at each of those nodes, and it comes out and figures out where your finger is based on how the capacitance changes. And it works really well because of the fact that this is a grid arrangement where you have individual measurements at each point. Unlike, say, a resistive where you're measuring the resistance of the entire touch panel, with Pcap you're measuring the resistance at each individual square, almost like a key array, except that that's a more Boolean concept. Here it's more like an analog key array. You're measuring how much capacitance changes at, say, 3 or 4 nodes, and then you can interpolate where the finger is in between those nodes. One of the issues, of course, with that is that you have to have something that's actually going to change the capacitance. So Pcap does not pass the poke it with a stick test, because a stick isn't going to be electrically conductive and isn't going to alter the electric field. So that's why sometimes when you're using a glove or you have just a plastic stylus or something, it doesn't work with your cell phone because it's not a conductive component. Now I mentioned that there are a couple of different electrode patterns that you'll see. There's what, first of all, we call coplanar, which means basically the drive and the sense electrodes are on the same physical plane. There's one layer conductor and the electrodes share that layer. And in this particular drawing you see here, this is a diamond pattern, which is pretty obvious where the name came from. Each individual electrode is a square that's been rotated 90 degrees to make a diamond. In this case, the blue electrodes might be the drive electrodes and the red electrodes might be the sense electrodes. And it can be either way. In terms of the actual design of the electrodes on the material, it doesn't really matter. It's all about the controller and whether it has more drive electrodes than sense electrodes or vice versa. So either way you think about it, essentially you've got these rows of drive electrodes and rows of column electrodes. But of course, the inherent issue is they're coplanar, so they can't touch. So how do you form that connection through the electrodes? You have to add what are called microcrossovers. These are these little tiny metallized conductors that basically bridge over one set of electrodes to connect the other electrode. So in this case, the way I've shown it, I'm bridging across the blue electrode to join the red electrodes into individual columns. And each of those little pieces is essentially a conductor with some kind of insulator underneath it so that you can put it down on the film. Typically this is done on film. And that allows you to bridge across and create your rows and columns. The difficulty with that is, of course, that no matter how small these individual microcrossovers are, and they're typically 2 to maybe 5 microns, they still interfere with the light transmission from the TFT, and they do to some extent degrade the optical quality of the touch panel. It's not terrible, and they're very difficult, if not impossible, to see with the naked eye, but it is a measurable effect. You can take a touch panel without microcrossovers and one with microcrossovers, measure the transmittance of light, and actually see a difference between the two. The other version that we talked about is 2 separate layers of electrodes. So in this case, you actually have 2 completely separate conductive layers, separated typically by some kind of adhesive. And they are laid out in various patterns. The easiest way to think about it is just straight lines, although there are some variants to that with stars and circles and all kinds of little things that you can do. But essentially the concept is the same. It's just a grid. You're just laying out, one direction and then another layer that's exactly perpendicular to that direction. And then, of course, the great thing about this is they're 2 separate layers, so you don't need microcrossovers. The downside of that is it's thicker because you have to have 2 conductive layers. So let's talk about the benefits and the cons of Pcap. First of all, the pros are that it's extremely durable. Because you can do this bezel-less design, you can essentially design a product that is completely sealed if you want. And we have customers, for example, that use this for medical products that are in operating rooms that can actually be splattered with blood or saline products or whatever during an operation. And when they want to clean it, they just take the most caustic alcohol sort of cleaner you can imagine, spray it all over the thing, just wipe it down. And it's no problem. They're just wiping off glass because they're not making actual contact with anything that's working, any of the conductors or electronics. You can also, because of that concept, you can do a bezel-less design because now you can have one piece of glass around the entire top of your display, one solid sheet. Because again, the whole idea is we're projecting this electric field, so we can project it through whatever we want. Glass, a piece of acrylic, you could even, in theory, even put it through a piece of wood, although of course that kind of ruins the idea of a touch panel. But it doesn't have to be opaque. The point is it just has to be able to allow the electric field to go through it. It's extremely accurate because of the layout of the electrodes and because of the interpolation and the very precise measurement of the individual capacitor values. You can actually get very accurate with these touch screens. A lot of the touch screens that we produce are accurate to, say, within 1 or 2 millimeters, which a typical finger is 8 millimeters, so that's basically an eighth of the size of your finger. And some of the consumer products, which have really tight electrode spacings, are even better. There may be a half millimeter, 500 micron kind of accuracies. You don't have to recalibrate it because, again, the whole idea here is you're measuring the capacitance of the 2 layers of the 2 electrodes, and they don't really move or change with respect to each other, especially if they're on glass. They're not going to change at all. If they do change a little bit, every time the thing powers up, it figures out what all the measurements are for each of the capacitors, and it can take that into account. And then it can also do background correction as it goes and say, okay, let me do a new scan now, nobody's touching it, and see whether or not it's changed because of humidity or whatever. And it's great optical properties, again, because especially if you implement it on glass. There's no microcrossovers involved, so it's very clear. It can be thin if you implement it as a coplanar design, which is, again, typically done on film, but it can also be done on glass. Or if you want to go the opposite direction, you can have it be very thick and very durable. Again, we have customers in the medical field who want to have a very heavy, thick product that, if somebody knocks over the display in the operating room, isn't going to break. So we have customers that come to us and say, I want a 4 millimeter thick piece of specialized heavy-duty Gorilla Glass or whatever. And we can make that work because all we have to do is change the design of the touch panel to get that field to project above that surface. So you can do very heavy-duty, durable designs with this if that's what you want to do. You also have the flexibility, again, of doing very thin, small designs if you want to do a handheld product. Now, the downsides of Pcap is that, first of all, you have an issue with the size. So I mentioned before that as the electrodes get longer, the resistance is going to go up. And so if you take a Pcap and try to blow it up to, say, 40 or 50 inches, you start to have issues. Because at that point, you're driving an electrode that maybe has 200 to 300K resistance, and it's just not going to work very well. You also have an issue with the time that it takes for the drive signal to propagate down that electrode. So the bigger it gets, the longer it takes for the drive signal to get to the end, and you can't scan the whole panel within that window of time. But if you stay within, say, 20, maybe even 30 inches, that's not that big of a deal. But you won't, for the moment anyway, see a Pcap, say, on that big screen that they use at CNN that's 60 inches. Pcap just really can't do that right now, at least not with the kind of Pcap we're talking about. There are other people that do projected capacitive panels where they sort of matrix them together and do weird things, but I'm talking about just sort of the normal Pcap. It also requires a dedicated controller, which can be a downside. It has to have that because the algorithms to do the interpolation between the individual capacitance measurements are very complicated. There are some people who have implemented Pcap on a generic off-the-shelf microcontroller, and what they will sell you is, they'll sell you their Pcap controller, but it's really just, a microchip part or an 18 mega from Atmel or whatever, and all they've done is added software to it. The thing is, if you do that, you lose some of the benefits of having dedicated silicon to do all the complicated analog measurements, because you're trying to measure capacitances that are in the 5 to 10 nanofarad kind of range, picofarad kind of range, and so it's very, very difficult to measure those values with off-the-shelf microcontrollers without using really long scan times and high count A to Ds. And that's one of the reasons, as I mentioned before, that it also tends to be more expensive, because you got to buy the touch panel as well as a controller to go with it. It also only works with conductive stylus or finger. So again, what I mentioned before, poke it with a stick, it's not going to work because the stick isn't conductive and won't absorb the electric field. And then finally, because it is an electric field product, it is somewhat susceptible to display noise, although there are ways around that. You can shield the touch panel, you can add noise canceling algorithms, you can do frequency hopping, and there are all kinds of ways to sort of dance around that issue, but inherently it is a problem that Pcap is going to be susceptible to outside RF fields, either from the TFT or other things in the room. Now I want to spend a couple of minutes talking about some of these specific pros and cons that we talked about to get into some more details. So we've already talked about the concept of a bezel-less Pcap, and that's one of the main reasons that people start to select Pcap, whether they really understand the technology or not. They go for it more for the industrial design concept. So let's talk about what that typical stack-up would be. You would generally have a cover lens material of some kind with silkscreen on it. Most customers want to have some kind of silkscreen faceplate, whether it's got logos on it or buttons, outlined on it or whatever. So there'll typically be some top layer that's a piece of glass, and that will have some kind of silkscreen on it. Then adhered to the back of that with optical adhesive is the touch panel, and that touch panel could be a single layer of film that gets adhered with an optical adhesive. It could be a 2-layer glass touch panel that gets put on with an optical adhesive and has another adhesive in between the 2 layers to bond them together. There's several different terms that you'll hear when we talk about stack-ups. A lot of people, if you're reading through the articles, will say things like GFF or FF or FFR or whatever. Those basically are referring to how many layers there are and what those layers are. F will generally be film, G would be glass. So a GGG would be glass cover lens, a glass touch panel layer, and another glass touch panel layer. GFF would be a glass cover lens, a film layer, and a film layer. But if you see those kinds of terms, that's basically what you're seeing, how it's referred to. So you've got the cover lens, you've got your touch panel, and then of course your TFT. And some people will choose to bond the TFT to the touch panel optically so they get better characteristics out of it. Some people will just put a gasket around it and slap the TFT on. It really kind of doesn't matter. The only thing that really matters is the distance between the TFT and the touch panel. The closer those two are, the more you're going to have an issue with noise from the TFT affecting the electrical field and affecting the Pcap. But for the most part, we haven't really had an issue with that. We have some customers that want to put 100 microns or something between the two, and we can generally make that work without too much of a difficulty. Screen size. I'm running out of time, so I've already talked about some of this. I'm going to fly through some of this. I already talked about how screen size becomes an issue. You can't do too big with a particular screen size. Just as an example, we've actually built a 27-inch traditional Pcap, but so far that's the biggest we've done. We're looking at going bigger this year. Of course, that's always our thing, is to show a bigger touch panel at our big trade show every year. But the one that we have right now is 27 inches. Another thing you'll hear a lot about in terms of Pcap is ITO replacements. So a lot of people are trying to figure out how they can replace ITO. And again, you might see articles about this in various magazines, so I wanted to spend a minute talking about it. There are a couple of different ways that you can replace ITO. You can do metal mesh, you can have silver nanowires, which are basically a whole little grid of wires that just form a pattern, and then what you do is go in and ablate or remove pieces of that so you get conductors. You can do graphene. There are people that are doing carbon nanotubes, and there are, again, 5 or 10 other materials I could probably rattle off the top of my head, but these are sort of the biggies. The benefits of these are that eventually they will be cheaper than ITO. And I say eventually because we've talked to a lot of these guys, and right now they're not cheaper than ITO. They think they are going to be once they get the volumes, but right now they just don't have it. But the idea anyway is their projection is that they will eventually be cheaper than ITO. The biggest benefit really is that the resistance is much, much lower, because with a lot of these you're actually talking about a metallized conductor, silver or graphene or something else, and so you're actually getting a resistance along your electrode that is maybe, the whole electrode might be maybe 10 or 20 ohms instead of 10 or 20 K. And then with some of these, and again it depends on the technology, you also get higher optical performance. That really depends on what the material is they're using for conductor and how small it is. You generally have to have, for example, if you're using little pieces of metal or whatever, you generally want them to be less than a micron in size in order for them to not really be visible or have any impact on the user. And finally, as I already mentioned, very few of these are really available today. So you'll hear a lot about them, but there aren't very many products that are shipping with any of this stuff in it yet. One of the newest trends in Pcap is hybrid designs. So I said before we weren't going to talk about buttons and sliders, and that's true, we're not going to talk about it, but we are going to talk about the technology behind it, which is self-capacitance. Most Pcap panels use mutual capacitance. That is, again, you're forming a capacitor by having these two separate conductive pieces, whether they're side by side or on top of each other. Self-capacitance is the idea that you have an electrode that's driving a signal and the finger actually forms the other side of the capacitor. So when there's no finger there, the capacitance essentially is just whatever it is to ground, and then when your finger comes in, you're altering that capacitance. The benefits of self-cap is that you get a much bigger electric field because you don't have that second layer of the capacitor to sort of constrain you. The downside, though, is that it's not nearly as accurate because you've got this much bigger field and it's spread out all over the place. So a lot of vendors are doing now is combining both of those two measurements in the same controller. And this really gives you some really cool benefits. For example, gloves is one of the more difficult issues with Pcap. And what gloves really do, it's not the glove itself that causes the problem, it's the fact that it's keeping your finger from the surface. It's that your finger is really acting like a hovering finger because it's maybe 4 or 5 millimeters above the surface of the touch panel, and the electric field just doesn't extend that far. Well, with self-cap, you now have an electric field that will extend maybe 20, 30, 40 millimeters, and so now you can sense the finger in the glove. So in the mutual cap, you can take a measurement, you might see a tiny little bump there. In the self-cap, you take a measurement, you see a big bump, and so you can combine those two measurements and now come up with a very accurate location of the finger, even though it's in this very thick glove. There are a lot of other cool benefits you get with self-cap and Pcap, and again, I won't go through a lot of them. You'll find some literature. Atmel in particular is really pushing their new features for this, so on Atmel's website for their touch controllers, you'll find a little bit of information about it. Okay, I've got another 8 or 9 slides. I'm going to breeze through these, so if anybody has any questions, step in, but otherwise I'm just going to kind of plow through this, because most of these are the smaller technologies that aren't really being used much anyway. Digitizer, it's one of the oldest ones. The concept of a digitizer is you take a grid, some kind of conductive grid, and you put it underneath the TFT, and then you have a pin that actually has active components in it, and the grid and the pin are communicating with each other through the TFT and the cover lens, and you can figure out the location of the pin. The nice thing about that is you have an active pen, so you can actually do pressure sensing with a sensor on top of the pen. You can actually have buttons that go on and off, and you don't have anything between the TFT and you, other than maybe a cover lens. So it's a very good optical quality. It's very accurate, and you get these extra little features about having the buttons and the pressure sensing. Of course, the downside is you've got this active pen that you have to keep, and if you lose it, touch panel doesn't work anymore. The other downside is it doesn't work with a finger. It has to be this active stylus that actually transmits the signal. It doesn't matter what else you use, a passive stylus, an active somebody else's active stylus, whatever, it's not going to work. We already hit the pros and cons mostly in the discussion, so again, I'm going to kind of plow through this. You guys can read this over later on if you want. I'm sure Gary will make copies of this available. There's also a new idea now where you can combine Pcap and digitizer, which is kind of interesting. Here you're doing the same basic idea, but instead of having a separate active sensor behind the TFT, you're actually using the Pcap conductive layers as your sensor grid. So now you can do both finger and an active stylus with your Pcap touch screen, which is kind of cool. There's infrared. Basic idea, I'm sure everybody understands this. You just take some LEDs, you fire them across the touch screen, you pick it up with some photodetectors, and when there's a finger or something in the way, you can tell where the finger is. Not very accurate. It's good in that it'll sense anything, you can poke it with a stick, but it's bad in that it'll sense anything, you can poke it with a stick, and sometimes that's a problem. It also is an issue for the bezels that we've talked about. You have to have a very tall bezel area around the display because you've got all these photodetectors and sensors that you have to have around the top of the touch panel. Optical is basically the same idea, except that instead of having a bunch of IR LEDs and photodetectors, you just put cameras around the corners, CCDs. So you put cameras on the corners, you take some images, and you figure out where the finger is based on that. It's the same basic idea, it's just that you're doing it with a camera instead of LEDs. SAW, this is one of the more popular ones in the past. We're using a lot of ATMs and a lot of other kinds of products. And it's a very interesting technology in the way it works. So what you're doing is you put some transducers around the corners of the display, and you transmit a signal down the edge parallel to the display. And then you have reflectors based along that are at a 45-degree angle. The wave, as it goes down, bounces off each reflector at a right angle and goes across the touch panel. Then you re-reflect that down into a receiver. And the time for each of those waves is different, the traversal time. So your controller can then basically figure out, I have 20 waves, they occur at these particular time frames. When I have a finger in the way, I miss one of those time frames, or 2 or 3 of those time frames. So now I can go through and say, okay, I had a missing time frame here, and a missing time frame there, and if I put those two together, I get an X and a Y coordinate. Very popular because it's very robust. Again, these are used in a lot of ATM and outdoor applications. It does require a bezel design, so you have to have some kind of bezel with big outer area around it. But it's also robust in that, unlike a resistive, and you can poke it with a stick, you're not going to break it. It's also very popular because it's been around for 25 or 30 years. SAW's been on the market, I think, since 79 or 82 or something like that. It's been around forever. Surface capacitance. So this is an interesting idea. Here what you're doing is taking a conductive layer, putting it on top of the TFT, and then you're injecting an AC signal into each of the 4 corners. And as you do that, what you're doing is creating a current across the touch panel that is driven by each of the 4 corners. So when a finger comes down and touches the touch panel, it draws off a certain amount of that current, and you can basically measure the current draw at each of the 4 corners, and then again correlate where the finger is. Again, the whole issue with this, very much like a 4-wire resistive, you can't sense multiple touches with it, because if you have 2 fingers down drawing the current, you don't know which finger's drawing which current. All you know is that this amount of current's gone. So it's very hard to tell where multiple fingers are. Okay, so the most important thing really in here, how do I pick a touch technology? Well, first of all, if you have an ultra-sensitive cost kind of application, resistive is going to be your first go-to. I also list Pcap there only because it is coming down in price constantly, particularly with the volumes that are being driven by the consumer market. You might be surprised at the cost that you get for a Pcap, especially if it's a small one like a 3.5 or 4.3 inch. It is generally going to be more expensive than a resistive. I can't tell you how much. It will be somewhat more expensive. But you also get a lot of trade-offs for that. You don't have to worry about maintenance costs. You don't have to worry about it being damaged. You don't have to worry about cleaning it, et cetera, et cetera. But generally speaking, if you're really worried about cost, look at resistive first and maybe consider Pcap as an alternative. The second category is big, huge, giant touchscreens. If you're building 50, 60, 70 inch kind of a touchscreen, Pcap is not the right touch for you. Hopefully it will be in the next maybe 3 or 4 years as some of these ITO replacement materials come out. But today there just aren't really a lot of good options for that. So if you're going bigger than say 30 or 40 inches, you want to look at some of the older technologies like SAW, infrared, optical. And when I talk about optical, I mentioned cameras on the corners. There are also people that are doing optical with cameras actually mounted above, like you've seen in the mall where they had this display you could actually walk in and interact with on the floor, and there was a camera above that was viewing the area and figuring out where you were walking or poking or looking or whatever. And then finally, anything else, if it's not really, really low cost and it's not giant, really Pcap is the go-to thing now. There are reasons you might want to use one of the other technologies, especially if you have existing products or you get a good deal from somebody. But for the most part, Pcap is going to be your first choice for pretty much everything else. So, what is the central message of today's presentation? Well, the Pcap bandwagon's coming, and if you're not on it now, you probably will be soon.